Welcome to this particular DWSIM module. In this video, we are going to look at a small exercise using a binary system. Okay, so this is where I am at DWSIM simulation configuration wizard. I'm going to make it as I'm going to further next, and then this is the compounds wizard, wherein I'm going to take up two systems, that is two compounds. That is, number one is ethanol, right? So this is the component which I'm going to add. Now you can see the added components automatically it is being shown as ethanol. Now next one is I take up water and then I click this particular checkbox as getting added. Now you can see the difference here. What is happening here is ethanol and water are the added compounds. Now I go to the next. Now I have, because there is a water in this particular mixture and both are liquids, as you all know. We're going to work on this particular miscible mixture. Ethanol water forms an azeotrope, and then we understand through a particular diagram. Now I take up this thermodynamic package to be as the NRTL, and then I click add. Now the property package is added in this place. So what is the property package I have taken here in this? That is non-random to liquid equation of state. Now we choose VLE, vapor liquid equilibrium, because our system is a liquid mixture, and then when we are trying to generate some equilibrium, so it will be different temperatures between its bubble saturation temperatures. Now I go to the next. Now these are the unit systems window, system of units, wherein there is SI engineering, CGS, and engineering. We cannot change in all these four. If you choose one among these four, it will be fixed. Now, if I choose C5, there will be one set of unit system here. So I will be choosing temperature to be as centigrade and pressure to be as in the atmosphere, right? And you can see the molar flow rate to be as kilomoles per hour, mass flow rate is kg per hour, temperature is centigrade, and volumetric flow rate is meter cube per hour. So all the systems are in ready, because we are accustomed or we are acquainted with the atmospheric atmospheric pressure units. So that is the reason I have taken atmosphere Fahrenheit and centigrade as temperature. Now I go to the next. Now here, what do I do? What do I do is that I have to see this is activated. This is activated here. That is activate, double click to open editors. So I click next here, and as I click next here, so so I say now finish. Okay. So we are into the system configuration window, or we have done giving inputs, basic inputs to start building the flow sheet. Now I will take a material stream from this place and then keep it here, right? So and then I right click here and then I say zoom all. That means this becomes a little bigger. Okay. Now see that this particular stream, this is particular known as a stream one. It is named as stream one. Now if I double click this, uh, I there will be something called the stream conditions are open, that is known as material stream. I name it as feed, or feed stream, or I say I let us say feed, and that is a shortcut ETOH plus H2O, so that we understand it better. Now the temperature which is being taken is 25 degrees centigrade and pressure is 1 atmosphere. And let us take the molar flow rate as we are 100 kilomoles per hour. Okay. And if I have to press enter, then automatically the other conditions are calculated by this. See, mass flow rate is calculated, and then volumetric flow rate is calculated, specific enthalpy, specific entropy, all things are calculated, but we need to understand what is a mixture, binary mixture. So this is 0.5, 0.5 by default. So if I say accept changes, and then if I go to the conditions here, and then it is already the color of the stream is changed from red to the blue. Now, if I say again solve, so it is solved. Now you can see the time which is changing here. It is 9:48 p.m. 18 seconds. If I say again, so it is 9:48 p.m. 26 seconds. That means it is getting updated and calculated. Now, what is important to us? See, now the feed it is not changed. Why? Because I forgot to press enter here. So H2. Now I should say enter. Then you can see. Now we understand that ethanol water forms an azeotrope, right? Mm. That particular condition we need to actually explore in this. In this very, this DWSIM video or this session, we are going to understand how to generate the binary envelope. Now I go to the utilities. Mm, utilities, and then I say add utility, and then is material streams. I take binary phase envelope and with stream, and then you can see again, it's all enabled now. Blue colored one object type is what? Material streams, and utility type binary phase envelope, and then flowsheet object feed, right? So which stream in under which stream it has already has conditions, right? So this is the you know our area where we can generate what you call where we can actually adopt or where we can actually create the envelopes, binary envelope. I take it out here, and then this is what we have obtained here, right? Something is coming here which we don't want. Yeah, it's okay. Yeah. So now I make this little. Okay. So let me make this as a little bigger one so that, like this. Yeah. Let me see what I can do with this. Talk and flow sheet. Okay. So this is the area where now we are available. Now what we do, ethanol water, compound 1 is ethanol. By default, it is a light key component, and compound 2 is the water, which is a heavy key component. And envelope type, we choose TXY by default. This is VLE, and x-axis basis is mole fraction, and the pressure is given, and temperature is given. All things are given here. There's a fraction change. The step count is very important. For a smooth curve to obtain, step count is very, very important. If I take very less step count, the curve will not be smooth. So if I do this, then what do I do? There is something called, you can see at the bottom of this particular left hand side, you can see calculate. I say calculate. So if I say calculate, it has given me one particular TXY diagram, which shows it is an azeotropic composition. Okay, but it's very narrow. You can see, it's very narrow here. But to find where the two compositions are same, that is the challenge here. See, at azeotropic means what? The temperature is constant at one particular temperature. Both mole fraction of the ethanol and water will be equal. So if I move the cursor, you can see how it is changing. How it is changing. See, the bottom one is a bubble point curve and the top one is a dew point curve. If I go on doing this, at one place you see almost they will be same. So you need to actually do this like that. So it shows an azeotropic system. Now, if I same thing, if you want to generate the XY diagram, and then same thing, let us see if it is able to calculate. Now you can see calculated. Now see, there is a small demarcation here. Now you can see wherein I can able to find that at one particular point wherein mole fraction of ethanol in the liquid phase as well as in the vapor phase, it is 0.875, which is that is beautiful here. Now we can understand through NRTL model, we are able to generate vapor liquid equilibria in both phase diagram. That is, one is XY diagram and another one is TXY diagram. TXY is pressure is constant, and we have generated TXY diagram. and we could able to identify what is the azeotropic point better with XY diagram rather than the TXY diagram. That is also that is also okay, but if you have to zoom in and then find out. In the similar fashion, we can take another thermodynamic property package and also generate certain, such type of equilibrium curve, and we can compare and this azeotropic point with the given literature data. With the literature, of course, here it shows it is 87.5% of the azeotropic composition is 87.5%. But with the what you call literature, once we compare, then you have to judge which model is giving the particular azeotropic or which near to the literature. Azeotropic composition for which model is near to the literature data, literature value, that model is our expected model to continue with other operations of the design and other things, right? So this is what is about generation of the vapor liquid equilibrium data that we have generated at constant pressure, so it is known as isobaric VLE data. Okay, we will see in other video how to generate other data, and then we'll compare in one particular what simulation with other models also. Okay, see you, and then hope you have understood how I've generated when the step-by-step process. I request you all to actually make an attempt to generate such a diagram with the conditions given, and you can change the pressure, temperature also, and you can observe how the vapor equilibrium curve is changing and how the azeotropic composition is also changing, right? And yeah, hope if you have liked the video, please like it and then share it across with your friends, and do subscribe for more such videos.